how to use the Gauss-Jordan Elimination method to solve a linear system. So in the last lecture we have seen how to use the Gaussian elimination method, the Gaussian elimination method to solve a linear system. In this lecture we will see the Gauss-Jordan elimination, which is a variant of the Gaussian elimination method. So for the Gaussian elimination method we try to get the row echelon form of the matrix A. In this method we try to get the reduced row echelon form. So the reduced row echelon form is matrix. So here, for example, in the case of 3 by 3 matrix or any square matrix, it is the diagonal matrix. It is a diagonal matrix. However, in the case of Gaussian elimination, it is an upper triangular matrix, so with ones here and any values here and zeros here. So this is the reduced row or this is the row echelon form. However, the reduced row echelon form is matrix that have the form of ones here in the main diagonal and zeros elsewhere. So in any position that is not in the main diagonal is equals 0. So this is the reduced row echelon form of matrix, and we get it by doing some algebraic operations on the row echelon form of a matrix A. So let's see it in an example. So this is the same example that we have seen in the last lecture. So we get the row echelon form of this matrix, and we used it to use it with Gaussian elimination. But now we will continue our operations on this row echelon form matrix to get the reduced row echelon form. And to get it, we'll do more operations on this matrix and its corresponding vector b prime. So if we call this row here R1 and this one here, this row here R2 and this row here R3. So now our goal is to get matrix in the form of ones here and zeros elsewhere. So in the other positions we will get zeros here. Our goal is to get zeros here. So we already have zeros here and we want to get these 3 zeros here. So the first one, so we won't change this row, so it will be 0 0 1. This is R3 with any change. So we want to get this 0 at this position here. So to get it we will do operation between these two rows. So it will be R2. Here we have minus 5 over 4. If we take 5 plus 5 over 4 times R3, so this will be 0 plus 0, it is 0, and 1 plus 5 over 4 times 0, which is 0 also, or it is 1, sorry. And this minus 5 over 4 plus 5 over 4 times this one here, which is minus 5 over 4 plus 5 over 4, which is 0. And we must do the same here for the corresponding vector b double prime, for example, if we call it b double prime. So here we won't change anything, 1 here, and here it is 5 over 4 times, so 0 plus 5 over 4 times 1, which is 5 over 4. And to get 0 here at this position we will use R1 plus, or here if we have 3 over 2, it will be minus 3 over 2 times R3. So it will be 1 minus 0, which is 0, which is 1, sorry, and minus 1 half minus 1 half plus or minus 3 over 2 times 0, which is minus 1 half. And here 3 over 2 minus 3 over 2 times 1, which is 0. And we must do it also in the vector b, so it will be 1 over 2 minus 3 over 2 times 1, so it is 1 minus 2, 1 over 2 minus 3 over 2, which is minus 2 over 2, which is minus 1. And if we continue here, so we now get these two rows and we want to get the 0 here at this position, so this 0. For that, we will write these two rows here as they are, so it will be 0 0 1 and 0 1 0, and here it is 1. And to get 0 here, we must for example, this is R3 as it is, and this is R2 prime, if we call it here R2 prime, and this, for example, R1 prime. So to get the 0 here, we will use R1 prime, this row here. This row we get here, plus 1/2 R2 prime. So plus this row plus this row, so it will be minus 1/2 plus 2/2 plus 1, so it will be 0, and here 0. And also the same here for the corresponding vector, which is minus 1/2 here plus 1/2 here times 5/4, so it will be minus 1 plus 1/2 times 5/4. This will give us minus 3/8, so it is minus 3/8, and this as they are 5/4 and 1. So once we get this reduced row echelon form matrix, we can write the linear system as x1 here with coefficient 1, and this coefficient of x2 and x3 in this row are 0, so they will be 0, and this equals minus 3/8. And the same here, coefficient for x1 is 0, and also for x3, so the coefficient of x2 is 1, so it will be x2 equals 5/4, and the same here for x3, so it will be x3 equals 1. And these are the same solutions that we got in the previous lectures. Now we have seen the methods that we can use for any linear system, so the substitution methods and the Gaussian methods, and now the Gauss-Jordan method. In the next lectures, we will see the LU decomposition method and the Cramer's rule method.